Hi guys, no one can motivate you if you don't want to do it yourself. Moving objects of mass have momentum value. Flowing fluids definitely have momentum value. In the following question, water sprays from a nozzle located on the bottom wall of a water tank. Apparently the tank is on a trolley connected to a rope to the wall. Well, we are asked to calculate the tension of the rope. As an initial step, consider the following illustration. What happens when water sprays to the right? Of course the trolley will move to the left. In order for the trolley to remain still, the trolley is tied with a rope connected to the wall. This rope becomes tense. Well, we are asked to calculate the magnitude of the tension force of this rope. Before that, let's get to know the Reynolds transport theorem. To analyze the mass of a fluid, the value of n is the vector p, and the value of eta is the vector v. In the dynamics of motion, we know that the rate of change in momentum over time is the resultant force acting on a system. So, this quantity is the resultant force acting on the system. The force consists of F body and F surface. We have known these two types of forces in the previous video. This is the formulation of Newton's second law in fluid mechanics. Let's go to the discussion sheet. There we see some physical quantities such as the diameter of the hole and the depth of the hole. Just write the formulation of Newton's second law. In this equation there is a factor of control volume. We have to determine the control volume of the system. This control volume has a fixed form, so there is no change in the volume of the control volume. This factor is 0. Assuming that the fluid flow is uniform, then the integral form can be approximated from the sigma notation. Now we will identify what forces are acting on this system. The fluid has a certain weight. When the water sprays to the right, there is a force to the right. We don't know the force, because the force can be resolved into several component vectors. We can write the force as a vertical component and a horizontal component. In this case, we will analyze the force vector in the horizontal direction. So attach the subscript x to some physical quantities. The gravity is in the vertical direction. So in the x-axis direction, F body is 0. For the F surface there is only Rx. For this factor there are two holes. The top hole of the tank and the bottom nozzle of the tank. At the top hole of the tank, the water only moves downward, so the fluid has no velocity component in the x-axis direction, u1x is equal to 0. The velocity component in the x-axis is only found at the small hole in the bottom wall. That velocity is u2x. So the velocity vector v2 is u2x I hat. And the cross-sectional area vector is a2 I hat. Both of these vectors have the same direction. The dot product of the two vectors is u2x a2. Overall, Rx is equal to rho u2x squared a2. The cross-sectional area of the nozzle is a circle with a diameter of d. The area a2 is nothing but a quarter of pi d squared. The velocity of the water jet is given by the square root of 2gy. This is the magnitude of the force exerted by the water to the right. So what is the relationship between this equation and the tension in the rope? We know the equilibrium of the system. In a system at equilibrium, the resultant force acting on the system is 0. Since the momentum of the system is conserved, the force Rx will push the tank and the trolley as a whole to the left. Thus, at the connection point there is a force Rx to the left, and a tension force in the rope to the right. Mathematically, T minus Rx is equal to 0. T is equal to the value of Rx. Now, we can see the value of each physical quantity on the problem sheet. If I'm not mistaken, T is around 2.8 newtons. This is a fairly small force, but it is enough to make the rope tense. Happy learning, everyone.
I feel this pain, you already know. Turn that to gains, let my money show. I've got these things that I can't let go. Watch me turn this life into something that you can never own.